Look around you. The screen in front of you, the chair you're sitting in, the light coming through the window. What if none of it is base reality? What if the entire physical universe is actually a highly advanced digital construct? In 2003, philosopher Nick Bostrom formalized this idea into the simulation hypothesis. He argued that a civilization with massive computing power could run a simulation of their ancestors so perfectly detailed that the simulated beings wouldn't even know they were inside a computer. For decades, the main scientific argument against this idea was a problem of sheer scale. Skeptics pointed to a severe hardware limitation, often called the infinite computer constraint. Think about the processing power required to render a continuous, infinitely smooth fabric of spacetime. Tracking the quantum mechanics of every single particle in the universe down to the Planck scale would instantly overload any system. You would need a computer larger than the universe itself just to store the data. Because of these extreme processing requirements, physicists have historically concluded that a simulation of our universe is mathematically impossible to build. But the math might have just changed. A recent unexpected development in the field of information physics accidentally provides a workaround for this exact computational bottleneck. A 2026 postdoctoral analysis examined two newly unified mathematical frameworks, Tensor-Network Quantum Gravity, or TNQG, and the Predictive Tensor Control Plane, known as PTCP. The paper asks a very specific question: do these two models inadvertently validate simulation theory? The core thesis in the executive abstract is striking. The author concludes that while these frameworks don't inherently prove there is a creator, they strongly contribute to the theory's mathematical plausibility. They systematically eliminate the infinite memory problem. If we translate these complex physics equations into computer science terms, we are essentially looking at the precise software architecture required to code the cosmos. To build a simulated environment, your first requirement is to abandon the idea of infinite, continuous space. You need a foundational layer that can actually be computed. This brings us to TNQG. Reading through section 2.1, the document details a concept called a discrete state space. TNQG acts as a theoretical rendering engine, moving away from classical continuous physics. Instead of a smooth continuum, TNQG replaces reality with a pixelated network of nodes, chopping spacetime into computable units. Distance and gravity are mathematically rendered on the fly, calculated purely from the informational entanglement between these underlying nodes. If that sounds familiar, it's because it is exactly how modern video game engines operate. They calculate physical space and distance only when the underlying data needs to interact, saving massive amounts of computational overhead. But generating space is only half the battle. We still have the memory problem. How could any system track the exact multidimensional state of every single particle in the universe without crashing? The second framework, PTCP, solves this. Section 3.1 outlines a density model known as the Pattern of Life Tensor Train, or POLTT. This acts as the universe's ultimate memory compression algorithm, triggering an exponential drop in required storage space. Rather than recording the exact physical state of everything, the PTCP system stores heavily compressed probability fields. It uses a lazy loading mechanic. The true state of those particles is only unpacked and fully rendered when a subsystem is locally observed. Furthermore, particles traverse this system using risk-aware geodesic routing, meaning the universe actively computes the paths of least resistance to maximize efficiency. By rendering space strictly on the fly and lazy loading compressed memory, these mathematical frameworks demonstrate how a theoretically infinite universe can easily fit inside a finite computer system. So we return to the central question: do these mathematical discoveries definitively prove that our observable reality is an artificial simulation? The paper delivers a clear, explicit verdict: no. As outlined in section 4.2, providing the means to simulate a universe does not prove simulated intent. These frameworks lack ontological certainty. Translating the mechanics of nature into a computational model simply proves that the universe is mathematically coherent. It does not automatically mean a higher intelligence sits outside of time programming it. However, looking at the translation matrix table in the appendix, the overlap is impossible to ignore. Every major structural requirement needed to build a simulated reality directly aligns with the mechanical properties of TNQG and PTCP. We may never truly know if we are living inside a machine, but the infinite computer argument that skeptics relied on is dead. The strict boundary separating physical nature from algorithmic software has been permanently erased.